right, thank you for the introduction. Good afternoon, everyone, and thank you for coming to this session. The objective of my presentation today is to show why ISCO believes that ODU should be made resilient to interference and jammers. And you will also see how srsRAN is helping us with this vision. I'm gonna, let's see. Okay, I'm gonna start with a little bit of a background, and then we're gonna get into more technical stuff and some examples that I wanted to present. So if you think about it, any signal that appears in the uplink of the radio, whether it's a malicious signal or unintended signal, is technically a jammer. So only the maliciousness part is what makes a difference, whether you are being attacked on purpose or you are being jammed by something unintentionally. Some of the examples of the unintentional interferers are listed here on the slides. You may have some cross-border interference due to frequency allocation mismatch. You may have signals that are carried over large distances due to tropospheric ducting, which we're seeing a lot in the coastal areas of the United States. External PIM is certainly a form of a jammer that you see in a lot of Tier 1 operator deployments because of their frequency allocations. BDAs, harmonics of radio stations, and so on. We wanted in this presentation to talk more about the real jammers, and the example that I cover at the end of the presentation is about a real jammer scenario. I think when we think about jammers, the first thing that comes to mind is loss of communication, right? That's what everyone is thinking about. But I think it's loss of communication is just the first step, and you need to think about the impact of jamming that goes beyond just the loss of communication. So on this slide, you can see some of the impacts that could result from loss of that communication. I'm not obviously going to cover all of them, but I'll give you a couple of examples. So for example, if you have public safety communication being jammed, you may find yourself in some kind of legal situation that you would have to get out of. And this is also kind of obvious, but some of the other perhaps less obvious things is, for example, brand loss of your brand, right? Damage to your reputation. So you have, for example, an unscrupulous competitor that is trying to do something malicious, and as a result of that, your communication channel or your communication offering is being deemed as unreliable, and you have loss of your brand, loss of reliability, your reputation. And I think what is happening now, because of the proliferation of 5G networks and its use in a variety of private cellular applications, military applications, public safety applications, this threat of encountering any of these scenarios, I think, is increasing, and it's important to be mindful of that. There are some solutions on the market, and some of them have been talked about previously today, earlier today in the presentation, to deal with some kind of, in some kind of way, with jammers and interference. So, for example, if you're a big Tier 1 operator and you have at each cell site, you have multiple bands, you have a lot of spectrum, you can take an action of moving your subscribers to another band. It works great. Obviously, other bands are not being jammed, but you're losing access to the spectrum that you paid a lot of money for, and that's not really a good thing. The other concept that has been widely used is PRB blanking. PRB blanking can be done, PRB blanking is basically, hey, I'm not going to use part of the spectrum that has interference. And that can be done either manually through a configuration of the radio, or as presentation earlier today was, it can be done automatically. It works well. The issue with PRB blanking that it only works well if your interferer is much smaller than the bandwidth of your carrier, because you really can't blank your entire band. So that's an effective solution for some narrow band interference, but it's not an effective solution for a wideband interference. And also PRB blanking is not a very effective solution for situations where you have a very busy site. So you have a lot of traffic on your site, the site gets loaded, you need to allocate all of the PRBs, and so PRB blanking then simply limits your capacity. You can do physical resolution, right? For example, you can negotiate with cross-border and make sure that you coordinate your frequency or whatever else is causing your interference. But those things take a long time, sometimes months, sometimes years, to get resolved. So ISCO believes that all of these techniques are viable, but we are focused on cancellation. So we always have been focused on cancellation. And so our approach is basically, hey, let's, if we encounter interference, let's try to cancel the interference, because it's an immediate action, and it serves an immediate purpose of recovering the communication channel. A little bit about ISCO. ISCO has been in business since 1989. We've always been in the interference mitigation business. We're a small company located in Schaumburg, Illinois, which is Chicago suburb. And we built, I think up to this point, we built our own products that were installed in literally thousands of instances across tier 1 operators in the United States. So up to this point, our products were installed as a separate box, depending on when we designed the product and for which G. Sometimes the box was installed on the RF side. Sometimes the box was a combination of digital and RF mitigation. And sometimes our latest product, for example, is a purely digital product that operates on baseband and sits between the radio and the baseband processing unit. But now we're, I think, coming to a confluence of two distinct things. First of all, there is an open RAN kind of development and the transition from sort of closed systems to open systems. I know we all want it to be much faster, but it is happening. And at the same time, the operators are trying to reduce their cost and complaining about managing the boxes, extra boxes. It's a security issue, it's a management issue, it's a training issue for their employees. So we looked at that, we looked at the comments that we heard from our customers, and we decided that this is an excellent opportunity to try to integrate ISCO technology into, RAN provider products, like into the RU or into the DU, because then the product is self-contained inside an element that the operator or needs to have in the network, and it makes it very easy to deploy interference cancellation across the entire operator's equipment base. These are some of the examples that ISCO products are currently mitigating. Barrage jammers, which are basically noise waveforms, various narrowband jammers and interference sources, PIM, which is a wideband interference, non-malicious source, any kind of co-channel wideband and co-channel interference across borders, for example, with Mexico, where we may have different spectrum usage and allocation between the two countries. All right, so embedding ISCO into the RU or DU, this is how we kind of see this progressing from our perspective. So ISCO, we call this IMC block, which is interference management and cancellation, just sort of a marketing name for this. So ISCO can be inserted in the radio itself. And you can see the area on the slide where ISCO is inserted in the radio. And ISCO can also be inserted into the DU after the IQ data is recovered from the eSIP relink. srsRAN, I'm happy to say that srsRAN is helping us with both of these options. srsRAN is helping us with the option of ISCO being installed in RU by simply acting as a open source DU. And then you'll see the slides later, we're also integrating ISCO block, interference cancellation block, into the SRS DU directly. And SRS is helping us with that. IMC block basically has four major functions. We have spectral monitoring and detection, so we're just looking at the spectrum all the time. And if we detect interference, we take immediate action. We provide notification and logging to the rest of the RAN if that's required. And we also try to classify some interference. And in the case of classification that we do not recognize, we can store the spectral plots to be able to analyze them later in post-processing and improve our classification capabilities. So this is an example of how ISCO IMC is integrated into srsRAN DU. So ISCO block will be inserted into the PHY layer 1 area, and it will live there, basically automatically trying to cancel interference. The advantage of this is also that this block can be updated with the regular software releases. So basically a combined SRS, RAN, and ISCO release can introduce new capabilities into interference cancellation. Perhaps we have to adjust the capability of the canceller. Perhaps we have to add some new features, maybe support more antennas, more carriers, things like that. All of that can be done through software and updated as the customer receives their regular software load updates. So this is basically the components of the ISCO IMC block at high level. So we have IQ data correction, which performs the actual mitigation. That lives in the real-time process in the layer 1 area. And then sub-real time, we have other processes that are running where we do the waveform capture and analysis of the spectral view that we captured, identifying interference, and if we can find interference, basically applying and figuring out what the correction should be, and then applying the correction to the real-time block to be able to correct interference. So all of that is done automatically and without any operator involvement. All right, so here I'm going to go through a couple of examples of interference removal. So let me try to first explain what you see on the screen. So let's focus on the top, is it left box? So this is a spectrogram. So basically we capture about 10 milliseconds? That's about 5 milliseconds of the spectrum. And then on the top you can see the frequency response of the spectrum. And on the bottom you can see the actual spectrogram, which is frequency on the x-axis, and then the y-axis is time, and the color represent various power level that you are observing. So the blocky things are basically UE traffic, and this line that goes throughout the spectrum is a narrow band interferer. And then as you go from left to right, you can see 3 different snapshots in time where you can see that this interferer is changing, it's moving around, and then and so it's not always static. So it has to be dynamically tracked, which is what we do. And then if you look on the bottom, the same 3 panels, you can see that the interferer is being canceled without the impacting the underlying UE traffic below it. Okay. Here's another example. This is an example of PIM. So PIM is a wideband interferer in this particular case. And so if you look at the picture on the left, you can see these wide horizontal lines that go across the entire spectrum. You can barely see the UE traffic, maybe in the, let's say, lower kind of middle on the left. You can barely see the UEs poking through. So there are a lot of UEs behind the PIM. And when the cancellation is applied, now you can see a completely different spectrum. It's about 15 dB of cancellation. You can see significant amount of UE traffic that was basically hiding behind the PIM. But hiding behind the PIM simply means that the signal-to-noise ratio and performance of these UEs were not, were not good, and we're basically recovering that. Okay. All right, here's an example of kind of a comb-based comb kind of interferer where you have CWs that are hitting the center frequency of every PRB, and there is a UE traffic behind it, so you can see the comb very clearly on the left, and on the right you can see that interference is removed, about 29 dB or so of removal, and the UE traffic, which is the blocky thing in the middle, is still there. All right, so basically you are removing the interference, you are not sacrificing your spectrum, and you are recovering the communication link performance, or in some cases we have seen where after the interference is applied, the link is actually restored from being down. All right, so let's kind of go through the example because I think there are some important learnings in this example. So I'll describe the example a little bit. So we have N78 5GNR TDD UE. It's 40 megahertz bandwidth carrier. And it's connected to DU-CU core, and it's running an iPerf. So we can measure the throughput. And then on the right, we're going to inject an interferer, a wideband interferer. We call it prism jammer because we're capturing this interferer directly on the Mexican border that is used to jam cellular signals in their prism. Okay, so we're gonna put these two signals together in the setup, and we're gonna see what happens to UE traffic. We're sampling, so what you see here is the spectrum analyzer view, and we're sampling the both the interferer and UE uplink at exactly the same point. So first, we have just the UE. So what you see is on the left, you can see the UE traffic. In the middle, you see a constellation, uplink constellation. That's 256 QAM. This particular DU supports 256 QAM. And all the way on the right, you can see that the uplink throughput is approximately 107 megabits per second. So now we're going to introduce the jammer. So you can see that this jammer, I'm going to go back a little bit. So you can see that this jammer that you see on the right is now being superimposed on the UE traffic. Now what's interesting to note here is that the jammer is at a much lower level than the UE. I mean, I don't know if you can read the scale, but the jammer is about 20 dB below the UE. And yet you can see how the higher order MSCs and the constellation is suffering. The constellation is very noisy now. The DU can still maintain 256 QAM, but your throughput is now 75 megabits per second. So you lost about 30% of your aggregate throughput, right? And if you're sharing this particular channel with multiple simultaneous users, obviously their 30% loss is significant. So then we're going to increase the power of that interferer a little bit, right? So now you can still see on the left-hand side that the interferer is not exactly completely overpowering the UE. The UE still can be seen. I would say in this particular scenario, the interferer is maybe 5 to 7 dB below the UE. But yet the constellation is terrible. Now we are down to 16 QAM. The throughput is 32 megabits per second, and you lost about 70% of your uplink throughput. So this is kind of an interesting scenario that maybe people are not thinking about it. And because when we think about jammers, we think about this massive power that has to be applied to disrupt communication. But the reality is that even a relatively low power jammer can significantly affect higher order MCSs and the throughput. Okay, so what we're going to do now is we're going to turn on the ISCO cancellation on, right? This is a low power case, what we see before, right? And so with the ISCO cancellation on and the jammer being about 20 dB below the UE, the constellation is pretty clean. The throughput is basically goes back to 107 megabits per second. So we recovered the throughput in the low power case. And then in a situation when we raise the power of the jammer and we apply ISCO cancellation, the 256 QAM is still maintained. So we went from 16 QAM without ISCO cancellation on to back to 256 QAM with ISCO cancellation on, and the throughput is pretty much the same as it was. So I wanted to put these cancellations side by side for you so you didn't think that I just copied and pasted good cancellation plots on the slide. So you can see that on the left-hand side, this is the baseline cancellation. This is the baseline without cancellation and no interferer. In the middle, you see the degraded constellation due to jammer at higher power. And then ISCO recovery is shown on the right. Now you can compare the ISCO recovered constellation and the baseline constellation. You can see that ISCO recovered constellation is a little bit more noisy than the baseline constellation. But yet, the noise is not sufficient enough to degrade 256 QAM capability of the DU to process the signal. Okay, so we did a similar test in the OTA environment. This particular example was ISCO integrated purely in the DU with software. Yeah. We performed this kind of similar test at one of the national research labs in the OTA environment, and it basically shows the same kind of results. So you can see on the chart, as the interference power increased, the red line, the throughput has decreased significantly, and with ISCO cancellation on, which is a green line, the throughput was significantly recovered. All right, so in summary, ISCO believes that RF jamming threats are serious. The proliferation of UAV platforms that could be easily flown towards a particular site are very easily obtainable now. So we believe that the impact of the jamming of these 5G systems could be significant if there are bad actors involved. Having something like an ISCO block inside the DU, integrated in the DU, for example, is a great way of protecting your networks against these potential dangers. And we believe that if the interference cancellation is ubiquitously deployed across all of the DUs, then you will have the most robust network possible that can protect you from jammers and interference. I think that's it. Thank you.